Hello, and welcome to the lecture on 7.2. Today we're going to talk about addition and subtraction identities. Let's go ahead and start with a derivation of the cosine addition formula. When we say addition and subtraction identities, what we mean is that we're adding two angles in the input of sine or cosine or tangent. So suppose that we have our unit circle here. We have two angles on the unit circle, specifically this one here, draw in red. Call this one theta. And then we continue from theta to here. And we call this one phi. Now, I can also go a negative phi distance, which is what I'm going to do here in blue. Down here, this would be negative phi, because we're moving in the negative direction, meaning the clockwise direction instead of counterclockwise. What I want to do is draw a couple of lines here to here and here to here. The distance from here to here is theta plus phi units, radians or degrees, it doesn't matter. And the distance from here to here is also theta plus phi. So these two lines are actually going to be identical lengths. And that's what we're going to use in order to prove this. First, let's figure out each point. So here, this point here, we'll call, this one is going to be cosine theta, sine theta. Remember, on the unit circle, cosine is the x value, sine is the y value. This point here is cosine theta plus phi, sine theta plus phi. This point, of course, is just 1, 0. And then this point is cosine negative phi, sine negative phi. Recall that cosine is even, so cosine negative phi is actually going to be cosine of phi. Has the exact same value. Similarly, sine is odd, so sine of negative phi will actually equal negative sine phi. So this is the same thing. This point here is the same as cosine of phi, negative sine of phi. Now let's use that distance that we were talking about. So we said that we had that these two lengths were identical. Okay, so let's use the distance formula to go from this point to this point, which would be the length of this straight line. And that distance formula is going to be the square root of the x value minus the x value, quantity squared, plus the y value minus the y value, quantity squared. So we have cosine phi plus theta minus our x value here, which is 1, quantity squared, plus sine theta plus phi minus 0, quantity squared. So we just get sine squared theta plus phi. And that will be the length of this line. Now again, it's the same as the length of this line. So this is going to be equal to the length of this line. So we just need to find the distance formula between these 2 points to get the length of this line. So again, x minus x, y minus y. We do cosine of theta minus cosine of phi, remembering that cosine of negative phi is the same as cosine of phi. So I'm just replacing cosine of negative phi with a cosine of positive phi. Quantity squared plus sine theta minus sine of negative phi. But remember, sine of negative phi is negative sine phi. So we have sine of theta minus sine of negative phi, which becomes a plus sine phi. Quantity squared. Now I'm going to ignore the square roots because they don't do anything in this case. We can just square both sides. So what I need to do next is FOIL this out. FOIL this out, FOIL this out, and FOIL this out. We'll have cosine of theta plus phi squared minus 2 cosine theta plus phi plus 1 squared, which is just 1, of course, and plus sine squared theta plus phi. Now on the right side, again, we FOIL these out, so we get cosine squared theta minus 2 cosine theta cosine phi plus cosine squared phi. That's this first one. Plus the second one would be sine squared theta plus 2 sine theta sine phi plus sine squared phi. Now I know that's a lot, but I want you to notice a couple of things really quickly here. First, we have sine squared theta plus phi and cosine squared theta plus phi. Now these two things are being added together. Now since they're being added together, we essentially have the Pythagorean identity, which is sine squared, let's say x, plus cosine squared x is equal to 1. Now notice that our x in this case is just theta plus phi. If we replace x with theta plus phi, we have a sine squared theta plus phi, which is sine squared x, plus cosine squared theta plus phi, which is cosine squared x. So these two things will simplify to 1. Similarly, we have a cosine squared theta plus a sine squared theta, so that will be a 1, and cosine squared phi plus sine squared phi, that will also be a 1. So we have two 1s on the right and one extra 1 on the left. We have a 1 here, plus these two things becoming 1, we end up with 2 minus 2 cosine theta plus phi is equal to this and this becomes 1, and this becomes 1, so we have a 2 here, minus 2 cosine theta cosine phi plus 2 sine theta sine phi. And we're almost done. Now we just need to simplify a little bit more. We have a 2 on both sides. We can cancel. We can divide both sides by a -2 also. So we have a -2 here, which will go away. A -2 here, which will go away. And this will change sign to be a negative instead of a positive, because again, we're dividing by -2. So we end up with cosine theta plus phi is equal to cosine theta cosine phi minus sine theta sine phi. And we're done. Pretty straightforward. We now have the sum of two angles, and we can reduce that to a formula where we're taking the cosine and sine of a single angle at a time. So cosine theta plus phi becomes cosine theta cosine phi minus sine theta sine phi. To do the subtraction formula, all we need to do is replace phi with negative phi, cosine theta minus phi. So all I'm doing is replacing phi with a negative phi, which means I replace it with a negative phi here and a negative phi here. But remember that cosine of negative phi is the same thing as cosine of positive phi. So when I replace phi with negative phi for my cosine here, it stays the same. It just becomes positive again. So cosine theta, cosine negative phi, but this will become just cosine positive phi, minus sine theta, sine negative phi. Now also remember that sine of negative phi is the same thing as negative sine phi. We end up with cosine theta minus phi is equal to cosine theta cosine phi plus sine theta sine phi. Again, we get this plus because this becomes negative sine phi, and we would multiply it with this negative and we would get a plus. So we have our second formula. Let's recall the cofunction identity. A cosine of pi over 2 minus x is equal to sine of x. Now, I didn't prove it, but last section I told you can prove this graphically. Very straightforward. If you just use the graph shifting techniques on cosine or sine, you'll get the cotrig function for each of the copairs. But in order to prove sine of theta plus phi, what I'm going to do is rewrite this as cosine of pi over 2 minus theta plus phi. like this. So my x is being replaced with theta plus phi. Sine of x, sine of theta plus phi, cosine of pi over 2 minus x, cosine of pi over 2 minus theta plus phi. Okay. We're going to distribute this negative, and we get cosine of pi over 2 minus theta minus phi. And then we're going to regroup this a little bit. So I'm going to group it like this. Think of this as a single angle now. Now we can apply the subtraction formula for cosine. Because we have an angle, in our case, pi over 2 minus theta, minus another angle, phi. And this will be cosine of our first angle, which was theta here, but is pi over 2 minus theta now, cosine of phi, and then we have a plus, sine of our first angle, pi over 2 minus theta, sine of our second angle, which is phi. Now, again, we can see cosine of pi over 2 minus theta, cosine of pi over 2 minus x will become just sine of x, which means this becomes just sine of theta. So this is the same thing as sine of theta, cosine phi, plus, and again, we do the same thing. Sine of pi over 2 minus theta becomes cosine of theta, sine of phi. And I will formalize this on the next slide. But we can see we have sine of theta plus phi is equal to sine of theta, cosine of phi, plus cosine of theta, sine of phi. Now we can prove the subtraction formula very easily just by replacing a phi with a negative phi. I'm just going to write it on the next slide here. So we have our addition and subtraction identities. Sine of theta plus or minus phi will equal sine of the first angle theta, cosine of the second angle phi, plus or minus cosine of the first angle theta, sine of the second angle phi. Now I need to note, plus goes with plus, minus goes with minus when we're doing the sine addition and subtraction angles. So if it's sine theta plus phi, then we get a plus here. If it's sine theta minus phi, we get a minus here. And that flips for the cosine. So cosine theta plus or minus phi is equal to cosine theta, the first angle, cosine the second angle, minus or plus sine of the first angle, theta, sine of the second angle, phi. Now again, cosine theta plus phi this time goes with a minus. Cosine theta minus phi goes with a plus. And lastly, tangent of theta plus phi is equal to tangent of theta plus tangent of phi divided by 1 minus tangent theta, tangent phi. And then tangent of theta minus phi is equal to tangent of the first angle theta minus tangent of the second angle phi divided by 1 plus tangent of the first angle theta, tangent of the second angle phi. Now, these two I'm not going to prove. Very easy to show. It's a lot of algebra, but you just do sine over cosine just like normal, remembering that tangent of x is equal to sine of x over cosine of x. If you just replace your x with theta plus phi or theta minus phi, you can simplify to one of these. Now let's go ahead and apply this. So let's do an example here. Find sine of 75 degrees. So what we need to do here is we need to break 75 up into two angles that are on the unit circle that add up to 75 degrees. And I think the easiest way to do it is sine of 30 degrees plus 45 degrees. Pretty straightforward. And then we use the addition sign. You could also do a subtraction angle. like sine of 135 degrees minus 60 degrees. That would also work as long as they sum to 75 degrees and both angles are on the unit circle, you should be fine. In this case, these two are on the unit circle, but I think this is the easiest way to break it up. So we do sine of the first angle, sine of 30 degrees, cosine of the second angle, 45 degrees, plus, because we have an addition, sine of the second angle, which is 45 degrees, cosine of the first angle, 30 degrees. A lot of people swap this order. That's fine. I don't know why I like to keep my sines first and my cosine second. It's just a habit. I think most students write their cosine first and their sine second. That's totally fine. We can multiply in either order. It doesn't matter. Now, sine of 30 degrees is, of course, 1/2. Cosine of 45 is root 2 over 2. Plus sine of 45 is root 2 over 2. And cosine of 30 is root 3 divided by 2. Multiply straight across. 1 times root 2, we get root 2 divided by 4. Plus root 2 times root 3 is root 6. They have the same index, so we can combine them. Divided by 4. And then you can sum them together. Combine the two fractions because we already have a common denominator. I'm going to leave that part to you because it's a very easy step. All right, go ahead and try one now on the accompanying worksheet. Find cosine of 15 degrees by using an addition or subtraction formula. In this case, you'll have to use a subtraction. Let's now do another example, but with cosine and in radians. So cosine of 13 pi over 12. Now, the radian measure is a little bit trickier. You could always convert to degrees if you get stuck, but I don't recommend it. I think it's in bad form to convert between the two angles. Now, if you get stuck, obviously do it if that's the only way that you feel you can get the right answer. But I think there's an easier way when we do this. So what we need to do is we need to be able to reduce this because 12 is not on the unit circle anywhere for any of the radian measures. So we need to get them to be either 6s, 4s, 3s, or 2s in the denominator. What we want to do is we want to break this up into two fractions. And I'm going to use a plus here, but again, you can use minus if you need to. Actually, I'll do it two ways. We'll do it two ways. So we'll do the plus first. Now, what I want to do is I want my numerators to add up to 13 pi, but with the added condition that they reduce my 12. So I can't do 7 and 6 pi, for instance, because if I did 7 pi over 6, or 7 pi and 6 pi here, sure, they both add up to 13, and this is a correct breakdown, but 7 pi over 12 is not on the unit circle, so we would be in the exact same situation, and we don't want to do this more than one time if we can avoid it. What you want to do is you want two numbers that add up to 13 pi, but those numbers also simplify with 12. So for instance, we can do 4 pi and 9 pi. Now, 4 plus 9 is 13 pi, 4 reduces with 12, and 9 reduces with 12. So we get numbers that are on the unit circle now. So this will become cosine. 4 pi over 12 just becomes pi over 3. And 9 pi over 12 becomes 3 pi over 4. And then we can just use the cosine formula. Now again, we have an addition. So this will become cosine of pi over 3, the first angle, cosine of the second angle, 3 pi over 4, minus, because we have a plus here, so we have a minus here, sine of pi over 3, the first angle, and sine of 3 pi over 4, which is the second angle. Cosine of pi over 3 is 1/2. Cosine of 3 pi over 4 is negative root 2 over 2. Don't forget your negatives where they're necessary. is a common mistake, so be careful. Sine of pi over 3 is root 3 over 2, and sine of 3 pi over 4 is root 2 over 2. So we end up with negative root 2 over 4 minus root 6 over 4. Right. Now I'm going to use this subtraction formula now, just as a helpful guide, just in case you were having trouble with subtractions. So I do start out the same way, something over 12 minus something over 12. Now I need these two things to sum to 13 pi still. So my first thought was maybe 20 and 7, but 20 and 7 doesn't work. 19 is prime, so that won't work. 18 and 5, but 5 doesn't work. 17 is prime, so we go with, I think, 16 pi and 3 pi. Looks like a winner. 16 pi and 3 pi over 12. Again, we simplify, so we get cosine of 4 pi over 3 minus pi over 4. This then becomes cosine of 4 pi over 3, cosine of pi over 4, plus, we have a plus now because we have a subtraction here, sine 4 pi over 3, sine pi over 4. Now, cosine of 4 pi over 3 is negative 1/2. Cosine of pi over 4, of course, is root 2 over 2. Plus, sine of 4 pi over 3 is a negative root 3 over 2. And sine of pi over 4 is, of course, root 2 over 2. We get the same answer, negative root 2 over 4 minus root 6 over 4. Just in case you were having a little bit of trouble with that one. So go ahead and try one now on the accompanying worksheet. Find sine of 17 pi over 12. This one I think you can use the addition formula pretty easily. I told you how to prove the cofunction identity before by just graphing. In this case, we can show the cofunction pretty easily by using the addition formula. So remember the cofunction identity. Let's go ahead and use cosine cofunction identity. So cosine of pi over 2 minus x is equal to sine of x. And we already know the addition formula for cosine. So I can just do this. Cosine of pi over 2 minus x is going to be the same thing as cosine of pi over 2, cosine of x, plus sine of pi over 2, sine of x. So try one. Show the cofunction identity. Sine of pi over 2 minus x is equal to cosine of x. It's just the other cofunction identity, the opposite direction. It's just as easy as the way that I did it just before. Just follow the outline. The next thing I want to talk about is using the sum and difference formulas with inverse trig functions. This is a bit tricky. A lot of students mess these up, so pay attention here. Recall, the output of an inverse trig function is an angle. So keep this in mind. This is really important as we go through some of these examples. It's nothing new. This is all information we should know already, but we're just combining concepts now. So let's find sine of tangent inverse of 4/3 minus cosine inverse of 12 over 13. You might ask me, how am I supposed to do this? I've never seen anything like this before. But remember your concepts. Remember what these things represent. And remember, the output of an inverse trig function is an angle. So think of this as theta and this as phi, because that's what they're going to give you, is some angle. So this is essentially saying the same thing as sine of theta minus phi, where theta, we're saying, is the output of tangent inverse. Remember, it's an angle. And cosine inverse outputs phi. So what I'm saying here is let theta be tangent inverse of 4/3. Now, do I know what that is? Do I know what angle that is? No. Do I care? Also no. It doesn't matter. But this is true if and only if tangent of theta is equal to 4/3. Remember, definitionally, the inverse trig function. Definitionally, if theta is equal to tangent inverse of 4/3, then tangent of theta is equal to 4/3. Similarly, we said that phi is cosine inverse. So we have phi is cosine inverse of 12/13. And again, definitionally, this gives us cosine of phi is equal to 12 divided by 13. I'm going to do this in separate colors now. I need to note to everyone that right now, because of the restricted ranges of tangent and cosine, we know that these two are going to be in the first quadrant because cosine is negative in the second quadrant and positive in the first quadrant, and we have a 12/13, which is positive, so it must be in the first quadrant. Tangent inverse is positive in the first quadrant and negative in the fourth quadrant. And because we have a positive 4/3, we know that this angle, theta, is going to land in the first quadrant. You have to be careful when you're moving forward and doing this a little bit differently with different problems. And in the next try one problem, you'll see what I mean, hopefully. I'll try to explain it when I get there. So let's go back to this and say that we have a triangle and we have our angle theta. Now again, I do not know what theta is. And again, I don't care. But I do know that the relationship with theta and the opposite and adjacent side is 4 and 3. So tangent of theta is opposite over adjacent. And since we have tangent of theta is equal to 4/3, we know the opposite side is 4 and the adjacent side is 3. So we can say that this is 4 and this is 3, and we use the Pythagorean theorem to get the hypotenuse, which is going to be 5. And similarly, with cosine, you should try this one on your own, but cosine, we have the phi angle here. Now cosine is 12 divided by 13. Cosine of phi is 12/13. Cosine is also adjacent over hypotenuse. So I know the adjacent side is 12 and the hypotenuse is 13. We have this and this. And then we use the Pythagorean theorem again to find the third side of the triangle. In this case, it becomes 5. Now what we're looking for is sine of theta minus phi. Well, I don't have theta minus phi anywhere. I have a theta and a phi, but I don't have the angle theta minus phi. So we need to break this down so that we have sines and cosines of just theta and just phi. So we use the subtraction formula, and this becomes sine of theta cosine of phi minus, because we have subtraction, sine of phi cosine theta. Now we're looking at sine of theta. Well, I have a theta angle, I just need to find the opposite over the hypotenuse because we're dealing with sine. Opposite over hypotenuse is 4/5. Cosine of phi, we have an angle phi here, so we do adjacent over hypotenuse, which is 12/13, which we also have over here, minus sine of phi, so now we need to find the sine of this angle, so we do the opposite over hypotenuse, so sine of phi becomes 5/13, and cosine of theta, this angle, so adjacent over hypotenuse, 3/5. Now personally, I don't like to simplify these because we're trying to combine everything, so we have 5 times 13, 13 times 5, that's going to be the same, 65 as a denominator. So I wouldn't cancel this 5 with this 5. Instead, I would just multiply. So we have 48/65 minus 15, also over 65. Yes, this reduces. No, you don't want to reduce it because we're subtracting. You're just going to have to find a common denominator again if you reduce it. So 48 minus 15 is 33 divided by 65. And we are done. All right, try one. Now these are complicated, so be careful when you do this one. Evaluate cosine of theta plus phi, where tangent of theta is equal to 12 over 7, but it's in quadrant 3. Remember, tangent of theta is positive in quadrant 1 and quadrant 3. So we have a positive value, but remember that this is in quadrant 3. So you have to be careful when you find your sine and cosine. And sine of phi is equal to 4 over 5. But phi is in quadrant 2. So remember, sine is positive in quadrant 2 and quadrant 1. But we have our phi is in quadrant 2. Now, how I deal with negatives with my triangles, when I draw my triangles, how I deal with negatives is I draw the triangle in the quadrant that we want. So we have quadrant 3 here, means my triangle for my tangent is going to look something like this, where this is my theta value. Now it's still just opposite over adjacent, but remember we're moving left and down. So our y value is negative and our x value is negative as well. So be careful when you label your sides for this one. And similarly for phi, I would draw my triangle in quadrant 2, like this, where this is my phi. Again, it's still opposite over hypotenuse. Just be careful when you label your third side because it's moving to the left. So our x value is going to be negative. All right, last example. Cosine of tangent inverse of x over 2 minus sine inverse of y. So we do exactly the same thing that we did before. We relabel this as theta and this as phi. So we have theta is equal to tangent inverse of x over 2. And phi is equal to sine inverse of y over 1. Y divided by 1 is the same thing as y, so we can just leave it like that. And these are true if and only if tangent of theta is equal to x over 2 and sine of phi is equal to y over 1. Then we can draw our triangles. Because we have variables, we should draw this in the first quadrant. So call this theta. Tangent is opposite over adjacent, of course, so our opposite side is x, our adjacent side is 2. So this, using the Pythagorean theorem, gives us x squared plus 4. Similarly, with phi, we have opposite over hypotenuse, so this would be y and 1, and this would be the square root of 1 minus y squared. This becomes cosine of theta minus phi, which of course becomes cosine theta, cosine phi, plus sine theta, sine phi. And then we just need to find cosine of theta, cosine of phi, sine theta, and sine phi from our angles. Cosine of theta, adjacent over hypotenuse, so this becomes 2 divided by square root x squared plus 4. Cosine phi, again, adjacent over hypotenuse, so square root of 1 minus y squared divided by 1, plus sine of theta, x over the square root of x squared plus 4, and sine phi, which is y divided by 1. So this becomes 2 root 1 minus y squared plus xy divided by square root of x squared plus 4. And that's it. Yes, I understand that these are tricky. You just need to practice these a bit. And remember the most important bit is to remember that the inverse trig functions output an angle. So if you can replace this with an angle, you can set everything up by just setting it equal to an angle and then applying the definition of an inverse trig function. And you set up a triangle and you're all set.
I want to make one more observation. Notice here that our angles are tangent inverse of x over 2 and sine inverse of y. Because our inverse trig functions have restricted ranges, the theta here is limited to either quadrant 1 or quadrant 4, and phi here is limited to quadrant 1 or quadrant 4 because the restricted range of tangent inverse is in quadrant 1 or quadrant 4. Similarly, the restricted range of sine is also in quadrant 1 or quadrant 4. So these two angles are limited to either quadrant 1 or quadrant 4. Notice here that theta and phi don't need to abide by the same restriction. Because theta is not in the form of an inverse trig function, theta can be any angle. It can be in any quadrant. Similarly, phi can be in any quadrant. Again, because it's not restricted by an inverse trig function.
Right, the last topic I want to cover is expressions in the form of a sine x plus b cosine x. Recall, sine of theta plus phi is equal to sine of theta sine phi plus sine phi cosine theta. Suppose that we know what phi is. Then cosine of this angle phi would give us some constant. Let's call that constant a. And then sine of phi we would also know, and we'd be able to resolve this, and let's call that constant b. Then we would have a times sine of theta plus b times cosine theta, which would be in this form. This is the idea for this form. The idea that we can change from this form back into the sum of two angles. Let me show you that we can always do that. Suppose that we have a triangle. Let's say that we know this side is A and this side is B. Then, of course, the hypotenuse we can find using the Pythagorean theorem is the square root of A squared plus B squared. Now let's look at the form A sine x plus B cosine x. And if we multiply and divide this entire thing by the square root of a squared plus b squared, then we have this. And if we distribute the denominator into this, we would end up getting the square root of a squared plus b squared times a divided by the square root of a squared plus b squared times sine of x plus b divided by the square root of a squared plus b squared cosine of x. And looking at this triangle, whatever this angle is, we know that the cosine would be a divided by the hypotenuse. So let's call this angle b. So now we can say, well, if we looked at cosine of phi, we would have a divided by the square root of a squared plus b squared. And the sine of phi would be b divided by the square root of a squared plus b squared. Those are exactly the constants that we have here and here. So we can rewrite this as just cosine of some angle phi, or some angle that gives us an a value here and a b value here, whatever a and b are for our particular constants for our particular problem. So we would end up with the square root of a squared plus b squared times cosine of phi sine of x plus sine of phi cosine x. Then we can rewrite this using the sum of angles for sine. And this would become square root of a squared plus b squared times sine of x plus phi. Whenever we have something like this, of the form a sine x plus b cosine x, we could rewrite in this form. The square root of a squared plus b squared times sine of x plus some angle phi. Now phi is a very specific angle. It's the angle that gives us the adjacent side A and the opposite side B, whatever those numbers are, whatever those constants are. Let's formalize this a bit. Sums of sines and cosines. If A and B are real numbers, then A sine of x plus B cosine of x is equal to K sine of x plus some angle phi, where K is equal to the square root of A squared plus B squared, and phi satisfies cosine of phi is equal to A divided by the square root of A squared plus B squared, and sine of phi is equal to B divided by square root of A squared plus B squared. Let's do an exercise here like this. Example. Write the expression in terms of sine only. Negative square root 3 sine x plus cosine x. Now, when we're trying to write this in terms of sine only, we're using exactly the property we just learned. So what I'm going to do is I'm going to draw a triangle, because it's helpful, where the adjacent side is negative root 3, and the opposite side is 1. Then when we find the hypotenuse of this triangle, we get the square root of 1 plus 3, which is equal to the square root of 4, which is 2. So we end up with this. We have this angle here. Then what we can do, just to show you a little bit more of what's happening here, is we can divide this entire expression by 2. Now, of course, we have to multiply by 2 as well. The hypotenuse in this case. Well, it will always be the hypotenuse. So we do 2 divided by 2, multiply the entire expression. Again, this doesn't change the value of the expression because we're multiplying by a value of 1. 2 divided by 2, of course, is 1. But if we multiply the denominator in, so essentially we're dividing both of these by 2, we end up with 2 times negative root 3 divided by 2 sine of x plus 1/2 cosine of x. Now, what angle gives us cosine equal to negative root 3 over 2 and sine equal to positive 1/2? Well, that obviously has to be in the second quadrant because sine is positive and cosine is negative. So we have cosine of phi is equal to negative root 3 over 2, and sine of phi is equal to 1/2. So since sine is positive, cosine is negative, we know we're in quadrant 2. Now that angle is going to be 5 pi over 6. If you look on your unit circle, you'll see the coordinate negative root 3 over 2, 1/2, which is 5 pi over 6. So phi is equal to 5 pi over 6. Now, if we were to do this a little bit slower, we could say, well, cosine of phi gives us a negative root 3 at 5 pi over 6 and at 7 pi over 6. So another possible phi would be 7 pi over 6. But sine of 5 pi over 6 is equal to 1/2, which is what we want. And sine of 7 pi over 6 is actually negative 1/2, which we don't want. So we know that it's not 7 pi over 6. It has to be 5 pi over 6. So we can rewrite this now as 2 times cosine of 5 pi over 6 sine of x plus sine of 5 pi over 6 cosine x. We can see that this is exactly the sum of angles for sine. So we end up with 2 times sine of x plus 5 pi over 6. And we're done. We've written it in the exact expression that we wanted. It's only in terms of sine. It just happens to be a sum of angles. Write the expression in terms of sine only. We've done that. All right, that's going to be it for today. I will see you all in the next lecture.
If you enjoyed this video, please like and subscribe. All Try One problems are on a worksheet linked in the description. The answer key and solutions are also linked in the description. If you want some free help, you can find me at twitch.tv/SkinnerPrincipal Link is in the description, as well as my Discord server.